We will do class 3 question 1 or exercise 1. Some of you asked me to record a video on exercise 1. Perhaps this was due to projector screen that was too small, and some of you guys were sitting at the back and couldn't see, most likely, on the Stata example. So let's try to do exercise 1, questions A, B, C. So I'll read the question. It says, using the data set college distance Excel, carry out the following exercises. Run the regression of years of completed education, ED, on distance to the nearest college dist for females only, and construct a 95% confidence interval for the slope coefficient. Right, so first I should import the file, this file. I'll go to File, Import, Excel. Now I need to tick this, Browse. It's this one here. Done. Right, so you know the variables, what they are basically. I don't have to go through them again. So question A, let's run the regression. Let's run the regression with all variables, I mean all observations, instead of splitting it to female and male. So when you run this regression, you just type reg ed dist, well, let's put robust, and enter. Yeah, that's the result. And this is something we had we got in the class in the week 1 and week 2 and following week, so week 3. And this is the confidence intervals, and you have the p-value showing us a statistically significant coefficient estimate of this value. Now let's filter out the males in the observations. As you know, this dataset is composed of 3,796 people's responses to a questionnaire. These are the questionnaire questions. Basically, each variable is actually a question in the questionnaire, original questionnaire. So this variable here, female, as a question asks a gender of a person. This variable black coded is basically a question about person's race, and this one is a nationality. Then this one is test score, I guess. This one asks for whether dad has a college degree or not, so on and so forth. So now let's filter out and take away, remove the male observations. Basically, the observations that are coded as 0 in this case, because female, if a person is female, in this instance, the female variable will take 1 and 0 otherwise. So 1 stands for female and 0 for male. So let's redo this, rewrite this regression equation we had before. So it's page up, we go to next to this and type if female equal 1. So we'll take now all the ones basically in the female variable and ignore the zeros, which are males. Right, this double equal, it means basically equal to 1. Not the single equal usually implies assignment of value to some variable. So here, that's how this data accepts it. So enter. Good. Okay, now here we go. We have a number of observations now 2070, which tells us there are this many female participants in the data, and this is the coefficient estimate or magnitude of this, and the confidence interval, 95% confidence interval, is this value. In EViews usually it's not given, and the question was asked when I think the question requires us to construct a 95% confidence interval. We don't have to do this in Stata, it just spits out as a default table value, so we don't have to do this. This is the confidence interval, coefficient estimate. So basically, if you were to interpret this, is more likely this, like this. For an extra or for additional 10 by the way, the distance is in tenths of miles, so for additional tenth of mile, for additional 10 miles, the education, number of years in education declines by 0.06 basically years. So the education is number of years, yeah, education in number of years. So it's a value or units of measure is years. So if you multiply this value by 12, you get in months, number of months a person would miss during the year, during the whole education, well, their education history, basically, I should say, because this includes the college education and high school education in among the students of university or college in the US. Right. So now let's this constant, as you know, when you're living next to the school, this constant implies basically you will have 14 years of education in total. So basically distance will be 0 then, because you're living next to the school or college means you will have 0 distance here, right? So this will be the number of years of education then, and this will decline because it's negative for additional 10 miles and additional 20 miles, so on and so forth. It declines by this amount for every 10 miles of distance from school. So this is when you have you live next to school or very close to school, in other words. Okay, this is for females. Now let's go back and change this to 0 to now remove the females from the list and then just run the regression for males. Right, so here is the result with the males, only 1726 of them here, and it's in magnitude. The effect size is higher, yeah, well, looks like boys a bit lazier than the girls, and effect size in confidence interval is also higher, with the lower bound was 0.10, here is 0.12, and the interpretation is the same, in the same way. So this is A and B answered in your question. Now in the exercise, number C says, is the effect of distance on completed years of education, so this effect of distance on education is different for men than for women. So is this effect basically statistically different? So these two effects, are they statistically different for males and females? So let's try to do a hypothesis test here. You need to do a hypothesis test. Let's go to the sketchbook. Right, I think I tried to do something. I think it must be classroom exercise. Right, do I have enough space? Yeah, looks like I do have. Right, let's start then. Now let's say we've estimated the coefficients, so let's say that beta f hat is equal to, what is the value there, 0.08, so minus 0.08, and beta m hat, this is for females, was minus 0.06, something like that, right? Now we'll leave it there for now, we'll need it at some point. Now let's develop our hypothesis. Hypothesis is this. Null hypothesis says, since we are testing whether the effects are equal, yeah, the estimated effects of coefficients are equal between male and female, and to test that we'll develop this null hypothesis, where our null hypothesis tells that they are equal indeed. Oh, sorry, this I shouldn't say. It should be without hat, because we are doing an inference here. So these are basically without hat. We are trying to test the hypothesis for the population betas, not the sample betas. We will simply use the sample betas to make inference about population beta. That's why the null hypothesis or all hypothesis testing should be with which one is greater. We are not hypothesizing, so this is going to be a not equal sign here. So it's a no difference or difference kind of sort of hypothesis statement here with the two-tailed tests. So these are our hypotheses. This is a given value. Then, as usual, we have to construct a t-table or t-statistic for this to test hypothesis. So t in this case is equal to, oops, I think I should put it on a little bit of an angle, my tablet, so that I see I can write it. Okay, this is straight line now. Right, so this would be then beta f hat minus beta m hat. Right, so next would be then different standard error of the difference. Right, so that's what I need to calculate, and then compare this t with the critical value. So let's test at the 5% level. Alpha is 0.05. Okay, now I know what these estimates are. This beta 1 hat coefficient estimate is beta f is basically this value, but I don't know this. I need to estimate this. So standard error of the difference of beta f hat and beta m hat. Now well, we can make use of variance operator, where variance of sum of random variable, or this is a formula here, variance of a sum of two random variables or a subtraction is usually equal to, assuming that let's assume that they are not independent for now. In that case, what the variance operator tells is this: plus minus 2 covariance, covariance x and y. Now, when this is the formula for when x and y are not independent, in that case you will be using this formula. Or in the other case, which we are working now, is when x and y's are independent of each other and they come from different samples. In that case, this covariance term will be 0, because there is no correlation between them if they are independent. So that's the assumption about dependence here. As a result, dealing with this part, so we need to calculate this part. Now let's get rid of this. I was going to expand it, but I think I'll make another video on variance operators and variance of random variables and so on and so forth. Let's put this as a formula. We're not going to use it now. Actually, I should change color. Now, so for this case here, it will be variance of beta f hat minus beta m hat equals variance of beta f hat plus, now because of this part here, m hat. So now what is the variance of this coefficient here, this coefficient estimate? So we'll have to go back to Stata and we'll have to check that. So the variance is basically a square of standard error, or standard error is basically the square root of variance. So we'll go to this coefficient here. This is for females, this coefficient for females, and this has a standard error associated with it. So 0.018 is basically standard error. We'll now plug that into the formula here. So variance of that beta f hat basically is is a square of the standard error. So 0.018 squared, sorry, this, okay, plus, now for the beta m hat, we'll get it from here. This is the beta m hat here estimated, and 0.020, so 0.02 squared. So, and well, let me put it down this way then very quickly. I don't know, I'm sure you understand this, but just in case. So the formula is this: variance of beta f basically is equal to standard error of beta f hat squared. Yeah, it's a usual formula. I mean, the formula that you had in the basic statistics course, and this would be equal to I think I need a calculator here very quickly. I'll have to do this in some way. So 0.018 times 0.018 plus so it's basically around this number 0.0007. Right, so next let me just quickly test this. It seems to give us a slightly different value if we use this these values. Let me have a look. I should check the solution. Right, so the solution doesn't have it. So let's see. Should be this value. Let's go ahead, because it will take time otherwise if I carry on doing this double checks. Now this is the variance of the difference here of the random variables. Now we need the standard error of them, so we'll square root it. We'll just take the square root of that. So standard error, this doesn't mean anything. So standard error of beta f hat minus beta m hat is basically square root of this value. And wait a sec, very quickly, this would be equal to 0.027, around this number, around about this number then. Right, so you can double check this in case I made a mistake here. Next, let's calculate the t now. We have all the ingredients. So t is then bf hat, which is minus, okay, this is actually 6 here, this is 8. Right, so you see it's easy to make a mistake if you are paying attention to details. Right, so done. And I think let me do very quickly this calculation. Missing the bracket again. So the result is 0.74. That's 4. That's 7 here. Oh, okay, be careful. Done. Now, now let's. This is actual t. T-statistic, so we call it t actual. And at 5% significance level, t star, t critical, as we know, is 1.96. And given that this is greater than t actual, we basically fail to reject the null hypothesis that beta f is equal to beta f. And this implies basically that there is no statistical significant difference between the effect of distance on education of between male and females, basically their responses, I should say. Right, so now Do we have any other question in that? So the effect of basically question number two. Okay, no more questions. So let's make a conclusion. So basically the effect of distance on education, or number of years of education for women is not different from the men's, not statistically significantly different from that of men's basically. Now I will conclude it here, and I hope it was it won't take long time now to watch. I try to minimize the time. Initially I had 30-minute, 40-minute videos. I'll try to minimize them. It's 20 minutes, so it's still a long process basically. Just to explain this 10-minute long exercise, I'm taking 20 minutes, so I should be more efficient, more effective now with practice. Hopefully this will help you. Right.